Hello everyone. Today we're going to be talking about Physics 253, Week 4, problem number 24.39. In this problem, we are tasked with finding the excess charge at the surface of the Earth given the electric field strength at the surface. So just looking at the problem here, there's a few things that we want to note down. First of all, we have that the electric field at the surface is pointing downwards. This is going to simulate a negative electric field, so we're going to have our electric field pointing towards the Earth, similar to the problems that we were doing last week, in which we had a charge, for example. Let's say that this is a positive charge, and it's going to be emitting a positive electric field going away from it in all directions. So with that in mind, we can go ahead and get into the problem. So starting off, we want to note Gauss's law. So Gauss's law, in our case, as mentioned in chapter 24.4 specifically these problems, or these examples, we have our flux of our electromagnetic flux given by phi E as the electric field times the area of the sphere. We are also given that this same problem can be rewritten given the our value k and the area of a sphere to cancel, and the pi's cancel out and whatnot, and the radius do as well. So we are given this q, our charge q, over epsilon naught, our permittivity of free space. So just rewriting this equation, we can set these two values equal to each other to say that the electric field times the area of a sphere is equal to the charge q divided by the permittivity of free space. Then we can just rewrite that and solve for q, since we are solving for the excess charge. So just going ahead and defining some of our values here, we're going to be using the radius of the Earth, which is this value here in meters. We're also going to be using our electric field of negative. It's important that we note that it's negative 110 newtons per coulomb, and our permittivity of free space in farads per meter. And so when we're writing the equation, we want to go ahead and proactively rewrite some of the units so we know what we're working with in the end. Although we could just say, oh, we're working with charge, so it's going to be in coulombs. It's a little bit more helpful sometimes to make sure all the units match. So in our case, that means rewriting this newtons per coulomb to volts per meter. So there is a 1-to-1 ratio between newtons per coulomb and volts per meter, so we can do this without any conversion. And then we can go ahead and plug into our equation that we had here, where we are using our radius of the Earth and our permittivity of free space here. So at this point, what a volt and a farad, or a farad volt, is equivalent to 1 coulomb. So when this does all multiply out, the meters cancel and we are left with coulombs here. So this is going to be our answer. Q equals negative 4.97 times 10 to the 5th coulombs. And just a closing thought, sometimes some of these Gauss's law equations can get a little bit tricky just because there's so many different surfaces that we're working with. I'd say it's just important to make sure you've got the correct area for the shape that you're working with, or else you can get this problem very incorrect. So I hope you guys found this video helpful. Thank you very much for watching. Have a great week.